So think about what happened back in chapter 3. We learned a definition that had a limit in it for this new idea, a derivative. And then we learned later in chapter 3 some properties we could use to simplify derivative expressions. So here in chapter 5, we have this new expression, and it contains a limit, and it's a definition for what we're calling a definite integral, an expression for the area, the exact area under a curve. Now, let's talk about some properties we can use to make simplifying expressions with definite integrals in them easier. And the cool thing is we get to bring back some big ideas from geometry that maybe you haven't thought about for a long time. So that's the key to understanding these properties, is remembering that this notation, the one that's here, and then our new definite integral notation, they're just a notation for finding the area under a curve between two input values. So the first important property for simplifying a definite integral, if you change the order of the limits, then the result of the integral is the opposite. So remember, the limits are here, the a and the b. The a is the lower limit, b is the upper limit. If you switch the a and the b, so the lower limit becomes the upper limit and vice versa, then your area has the opposite value. And so maybe that doesn't make too much sense if we think about it in geometry, but think about that picture we were using. Let's think about this notation where it came from. Remember delta x? That was the width of every rectangle. And we computed that by finding the difference, b minus a, so the width of the whole interval, not subinterval, but whole interval, the whole partition, and dividing that by the number of rectangles we wanted to use. Well, think about what happens when you change the order of a and b. You're going to subtract, and you'll get a negative result, which you're going to divide by a number of rectangles, and all your delta x's are going to be the opposite. So you're multiplying the same heights by the opposite widths. It's just going to give the negative version of the answer you would get if you'd use the a and b in the other direction. So change the order of the limits and get the opposite definite integral result. Here's a second property. You're going to see this one all the time. If your upper and lower limit on your definite integral are equal, then the result of the integral is 0. So remember again what that means. This integral means find the area under the f curve between, usually it's a and b. Well, I can find that area. But what if I said find the area between a and a? You're essentially finding the area of a line segment, but a line segment is one-dimensional. An area needs 2 dimensions, so this area would be 0. If the upper and lower limits match, the area is 0. So a third property, if you have a constant multiplier in your integrand, so there's some number that multiplies, then you could factor that out to the front of the integral. So again, think about what this means in terms of area. This integral means find the area under the f curve between a and b. If I have a new integrand, which is some number times f, that means all my areas are going to be k times taller. So if all the rectangles are k times taller, you're going to multiply the height of every rectangle times k. That's the same as multiplying the area of every rectangle times k. So and you could just factor that out to the front and multiply the whole result by k instead. Multiply the result of the integral by k. If you have an integrand that is a sum or a difference, you can use that addition sign or subtraction sign to break up your integral into separate parts. So the integral of f plus g is the same as the integral of f plus the integral of g. Or the integral of f minus g is the same as the integral of f minus the integral of g. And then one more property, instead of adding or subtracting integrands, you can add or subtract intervals. So I think this last property really needs a picture to go with it. This says the integral from a to b of some function f plus the integral from b to c of that same function is the same as the one integral from a all the way to c. So what does that mean? That means if I find the area under f between a and b. That's this integral. And then I start right there from b, and I find this new area between b and c. And I add those two areas together. That's the same as if I had just found the area over that entire interval from a to c. The cool thing is, this property works even if b is not between a and c. So feel free to explore using this property even if b is out there or out there. Now we're going to do some practice problems in the next video to make sure that we know how to use these properties in a context.